We often believe we understand the world simply because it feels familiar. An apple resting on a table, a room wide enough for us to walk through, a body small enough to fit into everyday life. But what if those familiar things are only standing halfway along an invisible ladder stretching from a realm so small that the very idea of size disappears? To one so vast that even light cannot cross it in time. There is a quiet paradox in this universe. What we touch each day lies neither near the beginning nor close to the end. It happens to rest within a very narrow middle range, where the laws of nature become gentle enough for life to appear. Below this range, space itself may no longer be as smooth as we imagine. Above it, numbers grow so large that the very meaning of quantity begins to dissolve. So where does the true boundary of the universe lie? And why does humanity exist precisely within this fragile middle stretch of the ladder of existence? Stay with the channel. Gently tap the subscribe button. And let us listen together to a story that begins with the smallest things and slowly unfolds into a picture far larger than it first appears. An apple rests with us in space, steady and quiet. It is an ordinary apple, one we already know how to imagine. Its size fits easily into our shared experience. It is something we could hold, something our hands would recognize without effort. On the outside, there is nothing demanding our attention. A smooth surface, a gentle curve, a familiar weight. It is the kind of object our senses accept without question. Inside, though, there is already more activity than we ever need to notice. Within that small shape, there are many millions of living cells. Each one carries out its own quiet processes, not hurried, not announcing themselves, simply continuing as they always have. And beneath those cells, there is another layer still. Each cell is made from atoms, and there are unimaginably many of them gathered together here. We do not need to hold on to the exact number. It is enough to know that this simple apple is already a meeting place between what feels ordinary and what quickly becomes vast. We can let the apple rest in our minds as a reference point. Its size is easy to remember. It fits on a table. It fits in our memory. And because it is so familiar, we can allow it to stay still while everything else slowly expands or contracts around it. If we imagine dividing the apple's volume, first into larger pieces, then into smaller ones, and then into pieces too small to see, the act of cutting eventually turns into pure thought. There comes a point where tools no longer matter, and only ideas remain. Physics gives a name to one such idea. There is a smallest meaningful volume that our current theories can describe. It is built from something called the Planck length, a length so small that even the tiniest particles we talk about in everyday science seem large beside it. This is not something we could ever touch or carve out. It is simply a signpost, marking a place where our familiar descriptions begin to soften. If we filling the apple entirely with these smallest units of space, the count becomes overwhelming. The number grows far beyond anything we could list or track. We do not need to picture it clearly. The number is not there to be handled. It is there to suggest distance, a wide separation between the scales of life and the deepest structure of space itself. Thinking this way hints that nature may have a kind of flaw, a level below which the old idea of endlessly smooth space no longer applies. Near that flaw, concepts like distance and position lose their sharp edges. They blur slightly, as if seen through mist. The apple remains far above that region. But knowing that such a boundary exists quietly shapes how we think about the ladder of size it rests on. We can also let the apple guide us in the other direction. Instead of cutting smaller and smaller, we can begin to stack outward. We can use the apple as a unit. The way one brick helps us imagine a wall close to us. A human body occupies only a little more space. Roughly speaking, it might take on the order of 100 apples to match the volume of a person. The exact arrangement does not matter. What matters is the closeness. The apple and the human body belong to the same neighborhood of size, From there, the steps begin to widen. The Earth is far larger, its volume able to hold an enormous number of apples. The count grows quickly, and once again the precise figure is not important. What matters is how rapidly size expands when length increases by many powers of 10. Beyond Earth, the Milky Way stretches the imagination further. A vast system of stars and clouds and unseen matter, so wide that light itself takes many thousands of years to cross it. Measured in apples, its volume becomes a sea of units, far too many to picture individually. At this scale, the apple is no longer an object, only a marker. Beyond the galaxy lies the observable universe, the region light has been able to reach us from since cosmic history began. Here, the same quiet comparison can be made one last time. If we imagine filling that immense volume with ordinary apples, the number grows again, until numbers themselves begin to feel unnecessary. They are no longer instructions, only hints of distance. As we move through these scales, the rules that dominate each level gently change. At the scale of bodies and apples, chemistry and biology shape what happens. At the scale of planets, gravity becomes strong enough to mold landscapes and hold atmospheres. At the scale of galaxies, gravity patiently arranges stars into long-lasting patterns, circling together for billions of years. The apple remains quietly connected to all of these realms. It is small enough to belong to our daily lives, and large enough to sit many steps away from the deepest unknowns of physics. Different forces dominate at different rungs of the ladder, yet they are all part of the same structure. There is another way we sometimes describe this ladder: by counting not objects, but steps of size. Each step represents a factor of 10, a gentle widening or narrowing of scale. At one end lies the smallest length we can meaningfully name. At the other lies the widest distance we can observe. Between them, the apple finds its place. We do not need to hold the numbers in mind. It is enough to know that there are many such steps below us, and many above. Roughly speaking, the full span from the smallest to the largest covers a few dozen of these steps. The apple rests somewhere near the middle, not exactly centered, but comfortably within the same broad band as bodies, trees, rooms, and tools. This placement does not demand explanation. It simply is. The universe has a smallest scale we can talk about, a largest scale we can see, and a wide range in between where familiar things appear. The apple belongs to that range, along with us. And as we allow this image to settle, the apple can remain still on its rung of the ladder, while thoughts of the very small and the very large softly drift around it, without needing to be resolved. We can let our attention drift to a quiet scene from not so long ago. In one of NASA's wide, warehouse-like halls in California, a small rover moved slowly across the floor. It had wheels, cameras, and electronics packed into a simple frame. Nothing about the machine itself demanded excitement. What made the scene unusual was the distance between motion and intention. The commands guiding that rover were sent from far above Earth, from the International Space Station, where an astronaut sat calmly with a laptop, typing and clicking, letting signals travel down through space and atmosphere to reach the motors below. Each movement followed a gentle chain, a thought in orbit, a command turned into data, radio waves passing through antennas and cables, and finally a quiet response from the rover's wheels. At the same time, images flowed back in the opposite direction, returning to the screen in space. Hands and eyes were no longer tied to the same place as the machine. Action and observation were separated, then softly rejoined by instruments and measurements. It was a reminder that our reach often extends beyond our bodies, carried by tools that translate intention into distant motion. We can allow that image to fade into another kind of distance, one that opened not through hardware, but through ideas. Many decades earlier, a young student was deciding what to study. Physics, at that time, seemed like a mature field. It already described heat, light, motion, and energy with equations that appeared solid and complete. When the student, Max Planck, asked an older professor for advice, he was told that most of the important structures were already in place. Physics looked like a house whose main frame had been built. What remained, it seemed, was careful refinement, measuring constants more accurately, polishing details, and filling small gaps. To us, listening quietly, it can feel like a moment of calm confidence, a sense that the foundations were settled. At the same time, small mismatches were quietly appearing. Experiments measuring heat and radiation were beginning to show subtle disagreements with the formulas that had worked so well before. The differences were not dramatic at first. They appeared as gentle tensions between prediction and observation, especially when hot objects were studied in detail. Planck entered his studies within this atmosphere. He attended lectures by well-known scientists, absorbing established ideas, but he also felt the weight of traditional presentations. Rather than relying entirely on the classroom, he spent long hours reading original papers, following arguments slowly, making sure each step made sense. This habit gave him familiarity with existing theories without locking him into their most rigid forms. Eventually, his attention settled on a particular problem that many others had struggled with. Physicists were measuring the light emitted by heated objects using hollow cavities with small openings. The light escaping from these cavities carried a record of how energy was distributed across different colors. When plotted, this distribution formed a smooth curve. Finding an equation that followed that curve everywhere proved difficult. Some formulas worked well in one region and failed in another. One predicted an endless rise of energy at short wavelengths, something the instruments clearly did not show. Other adjustments softened that rise, but broke agreement elsewhere. The usual assumptions of classical physics resisted every attempt to reconcile them fully with the data. Planck approached the problem patiently. Using thermodynamics and statistical reasoning, he tried to preserve the familiar idea that energy could vary smoothly and continuously, adjusting details within that picture. Again and again, the results came close but did not quite settle into place. Eventually, he allowed himself a different assumption, one that did not feel natural at first. He supposed that energy was not exchanged in arbitrary amounts, but in discrete packets. For light of a given frequency, there would be a smallest unit of energy, set by a new constant multiplied by that frequency. Systems could hold energy only in whole multiples of this basic amount. With this assumption, the calculations changed. When the statistics were worked through again, the resulting curve followed the experimental data smoothly from one end to the other. The troubling divergence disappeared. The constant that set the size of these packets turned out to be very small in everyday units, almost invisible in ordinary experience. At first, it functioned simply as a mathematical step size, a bridge that connected theory with observation. Only later did it become clear that this constant marked a deeper boundary, a scale where old habits of thought no longer applied. We can let this story settle without forcing it into conclusions. A careful experiment, a willingness to adjust assumptions, and a patient calculation were enough to open a new way of describing nature. From the calm confidence that physics was nearly complete, a quiet shift emerged, one that would eventually reshape how we think about energy, matter, and measurement. And as we rest with this image, we do not need to follow every detail. It is enough to sense how, step by step, our understanding extends, not through sudden leaps, but through small, deliberate changes that accumulate over time. And then a single new constant has entered our shared picture of nature. Small when written down, yet wide in what it touches. It takes its place beside other fixed numbers that quietly shape the equations we use to describe the world. To understand why this one matters, it helps to notice the kind of family it belongs to. Some numbers in physics are chosen by us. Units like the inch or the meter, the pound or the kilogram, began as human agreements, tied to bodies, objects, or places. They were refined over time, made more precise. But they always carried the trace of a decision. Other numbers are different. The speed of light in empty space is one of them. The constant that measures the strength of gravity is another. These are not selected for convenience. They are encountered when we measure how nature behaves, and they remain what they are. In this second group, the numbers do not come with explanations inside our current theories. We measure them carefully. We place them into equations, and the equations work. But the values themselves are not predicted. They are taken as features of the world. The constant introduced by Planck belongs here. It is not a unit designed to suit human scales, and it is not adjustable. It appears when we look closely at how energy and light behave, and once its value is set by experiment, it quietly appears again and again across physics. What begins as a simple link between energy and frequency becomes part of how we describe atoms, solids, radiation, and fields. At the time this constant first appeared, the finest experimental tools had a clear but limited reach. Skilled hands and careful instruments could resolve lengths down to a few micrometers. With that ability, microscopes revealed bacteria, cells, and the intricate structures of living tissue. A hidden world had already opened at that scale, and it felt deep and rich. Yet the constant h pointed far beyond even this newly revealed micro-world. The length scales that naturally arise when h is combined with other constants are not just a little smaller than cells, but smaller again and again, through many steps of 10. Compared with them, even the microscopic structures of life are enormous. The constant did not merely refine what was already visible, it quietly gestured toward a region far below anything instruments could then, or now, reach. This contrast helps us sense the depth of the step that was taken. On one side stood the world revealed by lenses and careful preparation, a world of cells and fine grains of matter. On the other side lay a domain suggested only by calculation, where the basic ingredients of fields and particles reside. A careful study of the color and brightness of heated walls had, without drama, connected ordinary laboratory conditions to the deepest layers of physical law. The value of h itself is extremely small in the units we usually use. Written out, it is a tiny fraction of a joule multiplied by a second. Everyday events involve energies and times so much larger that this small step size goes unnoticed. This is why quantum effects do not announce themselves in daily life. The packets of energy exchanged by matter and light are minuscule compared with the flows involved in human-scale processes. They are present, but their fine grain is smoothed over when our attention narrows to very small systems. However, this changes. For single atoms, for electrons moving through solids, for light confined in cavities, the scale set by h becomes unavoidable. Energy can no longer be treated as a smooth continuum. It settles into levels and bands. Certainty gives way to probabilities. The constant marks, in a simple way, the point where this shift is no longer a minor correction but the dominant behavior. It sets the fineness of the quantum texture underlying the world. This same constant can be combined with others to form a set of natural reference scales. When we bring together the speed of light, which links space and time, the gravitational constant, which sets the strength of attraction, and Boltzmann's constant, which connects temperature and energy, we can construct characteristic units of length, time, and energy. These are known as the Planck units. They are not tied to everyday experience. They do not describe things we handle or observe directly. Instead, they mark extreme edges where our familiar theories begin to strain. The Planck length is unimaginably small, far below the size of even the tiniest particles we normally discuss. The Planck time is correspondingly brief, a duration so short that no direct measurement can isolate it. The Planck energy, by contrast, is large. A great concentration of energy associated with a single quantum. Taken together, these scales do not describe our ordinary world. They serve as quiet markers, indicating where our current descriptions of space, time, and matter may need to change. At distances much larger than the Planck length and times much longer than the Planck time, our best theories work remarkably well. They predict motions, interactions, and structures with great accuracy. As we imagine pushing closer to these extreme limits, however, tensions appear. One theory treats space and time as smooth and continuous. Another introduces fluctuations that resist being placed on a smooth background. When extended too far, the equations begin to produce infinities or contradictions, signs that they are being asked to do more than they can. For now, these scales remain far beyond experimental reach. The energies required to probe such tiny distances are vastly greater than anything our machines can produce. The times are far too short for any detector to resolve. In laboratories and in nature, as we observe it, processes unfold comfortably above these boundaries, where established ideas still apply. This leaves a genuine edge to our knowledge, not from neglect, but from the combination of extreme scale and theoretical limitation. The Planck units stand quietly at this edge. They do not tell us what lies beyond. They simply remind us that there is a boundary where familiar concepts fade and new ones will be needed. For the moment, we can let that boundary remain where it is, a distant horizon in our understanding, while our thoughts slow and settle, knowing that not every region of the universe needs to be entered tonight. Even so, measurements have already been pushed very far in the directions that are open to us. They have moved steadily toward higher energies, and down toward shorter times and smaller distances that our instruments can touch. From where we stand, these numbers already feel far removed from everyday experience. On the side of high energy, one of the clearest examples sits beneath the ground near the border of Switzerland and France. There, the Large Hadron Collider sends beams of protons around a circular tunnel and smashes them together. In its design, each beam can reach energies of about 14 trillion electron volts, usually written as 14 TeV. That number is difficult for us to feel directly. It helps to translate it into a simple picture. If a tennis ball could somehow be given the same energy in a single impact, the brief flash of that collision would be comparable in brightness to tens of thousands of Hiroshima-sized explosions. All of that energy would be compressed into one tiny moment. In the collider, of course, this energy is not delivered by a tennis ball. It is shared among many protons, their fragments, and the showers of new particles that appear briefly and then decay. Detectors placed around the ring record the traces these particles leave behind. The purpose of the comparison is not to alarm us. It is only to give us a sense of scale. Human technology, as we have developed it, has learned how to concentrate very large amounts of energy into very small regions of space and time. This concentration lasts for extremely short durations, and it remains under careful control. Even so, the energies reached in these collisions remain far below the Planck energy. Between the TeV scale of the Large Hadron Collider and the scale defined by the constants h, c, and g, there are many steps of 10. From our perspective, the gap is wide enough that the Planck point lies far beyond what even the most ambitious accelerator designs could attempt. The collider holds a record. That record, however, rests on a lower rung of a much taller ladder. Nature has, at least once, written a higher number in a different way. In 1991, A detector in Utah recorded a single cosmic ray particle with an energy so large that it exceeded the scale of laboratory experiments by many millions of times. Because the number was so striking, the event became known informally as the "Oh my God" particle. 2 sevens. Compared with a typical proton collision at the Large Hadron Collider, this one particle carried more than 40 million times as much energy. It arrived not from a tunnel built by us on Earth, but from some distant astrophysical source that has still not been fully identified. In this case, the Earth's atmosphere acted as the target. The particles struck the air high above the ground and produced a cascade of secondary particles. These spread outward and triggered detectors across a wide area. From the pattern of those triggers and the timing of the signals, the original energy could be reconstructed within our models. Here again, the image mainly serves to show scale. It reminds us that a single proton-sized particle can carry an amount of kinetic energy that, in daily life, would usually belong to much larger objects. Through its own processes, the cosmos accelerates particles far beyond the reach of machines we have built. Even this, however, does not reach the Planck energy. The distance between the energy of the "Oh my God" particle and the Planck scale still spans many orders of magnitude. In the language of powers of 10 that we use to orient ourselves, there remains room for millions or even billions of steps between them. On the high-energy side, both human-made colliders and the most extreme known cosmic rays remain well below the level where the Planck energy would become directly relevant. On the side of time, there are similar records. In 2020, a group in Germany used extremely short X-ray pulses to time an event inside a hydrogen molecule. From our point of view, the aim was to estimate how long it took for the influence of a photon to move from one electron to the other. The experiment did not follow the photon directly. Instead, it relied on an indirect method based on interference and phase. One can picture the setup in simple terms. A photon strikes the molecule and can eject an electron from either side. The two possible paths interfere, like ripples meeting on the surface of water. From the resulting interference pattern, and from careful modeling, a delay time can be inferred. In this way, a delay of about 247 zeptoseconds comes into view. A zeptosecond is 10 to the minus 21st seconds. This is a slice of time far smaller than anything our senses could ever register, yet still within the reach of our instruments and theories. Yet the Planck time is still much shorter. Its value, around 10 to the minus 44 seconds, lies about 23 orders of magnitude below the zeptosecond scale. Even when experiments reach times measured in tiny fractions of a billionth of a second, the gap to the Planck time remains vast for us. Current techniques can divide time into very fine segments, the segment marked by the Planck time, however, remains far too thin for any direct touch. There is also a record on the side of distance. Modern experiments probe how large, or how small, elementary particles might be. In some setups, single electrons are held in place by carefully arranged electric and magnetic fields. Their behavior can then be examined with extraordinary precision. From these measurements, limits can be set on the possible size of the electron. If the electron had a noticeable radius, certain effects would appear clearly in the data available to us. So far, none have been observed. The results only tell us that, if the electron has any size at all, it must be smaller than a certain upper bound. That bound lies around 10 to the minus 22 meters. Anything larger would already have left a clear trace. Anything smaller remains invisible to the methods we currently use. In this sense, the electron behaves as if it were point-like, at least down to that scale. Compared with this limit, the Planck length is still much smaller. It lies many orders of magnitude below 10 to the minus 22 meters. Physicists sometimes describe it as being a trillion times smaller, simply to help us feel the gap. It sits beneath the floor of present measurement, at a level where even the most refined rulers built from light and fields cannot reach. Taken together, these records show both how far measurement has gone and how much distance still remains. Energies in colliders and cosmic rays have climbed to extraordinary levels. Times have been resolved into fleeting intervals. Distances have been probed far below the scale of atomic structure, and yet, the Planck energy, Planck time, and Planck length still lie well beyond direct experimental reach. Between what has been measured and what those natural units quietly mark, there remains a wide band of scale untouched by experiment. From where we are, that band can remain as it is, a quiet region of the ladder, allowing our thoughts to slow and settle without needing to move any further tonight. Long before the language of Planck units settled into place, another kind of limit was already forming quietly in the background. It was not a limit of instruments or machines, but a limit on how clearly the world can ever be known. From where we stand now, it feels less like a sudden discovery and more like something that had always been waiting to be noticed. In the early 1940s, during the years of the Second World War, Werner Heisenberg traveled to Copenhagen. Denmark was under occupation at the time. His former teacher, Niels Bohr, still lived and worked there. The two men met and walked together, speaking privately. Later, they remembered that meeting in different ways. The subject of nuclear weapons was present in their conversation, yet the purpose of the visit never became fully clear. Some accounts suggest that moral concerns were at the center of the discussion. Others read the same encounter as connected to the effort to build such weapons. What is known remains simple. They spoke. They did not fully understand one another. After that meeting, their relationship never quite recovered. They did not return to the conversation to settle what had been meant. Letters, notes, and later interviews have been examined many times. Yet the intention behind that walk through Copenhagen remains uncertain. Even here, in the life of one of the founders of quantum theory, there is a gap that cannot be closed with confidence. This personal uncertainty sits beside a scientific one that carries Heisenberg's name. His work on quantum mechanics led to a clear statement about the limits of knowledge itself. Certain pairs of physical quantities cannot be known with unlimited precision at the same time. This is not a story about fading memories or missing records. It is a statement written into the mathematics of the theory. In quantum physics, position and momentum form one such pair. Position tells where something is. Momentum tells how it is moving. The uncertainty principle says there is a lower bound on how precisely these two can be specified together. When position is sharply defined, momentum spreads out. When momentum is tightly constrained, position becomes uncertain. From our point of view, no method can force both uncertainties to vanish at once. An early way of picturing this relied on light as a probe. Imagine trying to locate a very small particle using something like a microscope. To see more clearly, light with a shorter wavelength is required. That light carries higher energy. When it interacts with the particle, it can disturb its motion. Using gentler light reduces the disturbance, but also blurs the image. In this picture, the act of looking becomes part of what shapes the result. Over time, this view deepened. The uncertainty was no longer understood as a limitation of tools alone. It arose from the structure of the quantum description itself. Even with an idealized measurement, the spread would remain. The limit does not come from imperfect skill. It belongs to how nature behaves at very small scales. Planck's constant appears directly in the relation that connects these uncertainties. It sets the scale of the minimum spread that cannot be crossed. In this sense, h gives a measure of how fine-grained the quantum world is. If its value were smaller, the world would behave more like the classical picture we are used to, where position and motion could, in principle, be known together. With the value that nature has chosen, that limit is fixed, and it cannot be bypassed. This built-in softness does not stop with single particles. In quantum field theory, the basic objects are fields that extend everywhere. There is a field associated with light, a field associated with electrons, and others beyond that. Each field has values and rates of change throughout space. The uncertainty principle applies here as well. The result is that a field cannot be completely still. Even in what is called the lowest energy state, fluctuations remain. These are often referred to as vacuum fluctuations. They are not disturbances on top of an otherwise empty background. They are part of what the background itself is. Each mode of a field carries a small amount of energy that cannot be removed. From where we look, the field is never fully quiet. Because of this, empty space in the quantum sense is not truly empty. It contains small, restless variations that never entirely fade. For very brief moments, these variations can give rise to pairs of particles that appear and disappear again. The details are technical, and they do not need to be held in mind. What matters is the impression that some activity remains, even when nothing obvious seems to be happening. Now the picture can be extended one step further. Space and time themselves may not be just a stage on which fields exist. In general relativity, energy and mass shape space-time. Geometry responds to what it contains. If energy fluctuates even in regions we would normally call empty, then, at least in thought, space-time itself cannot remain perfectly smooth at the smallest scales. At human scales, and even at the scale of planets and stars, space-time behaves smoothly. Distances can be measured. Paths can be traced. The underlying texture does not matter. But near the deepest scales, suggested by fundamental constants, quantum effects in both matter and gravity are expected to become important. In that regime, the familiar picture of space-time as a smooth surface begins to soften. One way to imagine this is to think of a surface viewed from different distances. From far away, it looks calm and flat, like a lake on a still day. As the view draws closer, small ripples appear. At the deepest level, the surface no longer looks smooth at all. It resembles a restless foam, with tiny features forming and fading. This image is often called quantum foam. In this mental picture, space-time is filled with fleeting distortions. Small loops and twists form and vanish. Very tiny connections, sometimes compared to tunnels, may flicker briefly before disappearing. This is not a photograph of reality, but a way to express the idea that space-time itself may have a granular character at its base. Here, a tension appears. General relativity relies on a smooth geometry. Quantum theory insists on fluctuation. Placing the two together suggests that geometry should fluctuate as well. Yet a complete theory that unites these ideas has not been finished. The image of quantum foam remains a hint rather than an answer. This naturally leads to a quieter question. If space and time are restless at their deepest level, how do the large, stable structures we are familiar with emerge? Galaxies, planets, and everyday objects all depend on a space-time that behaves predictably on their scales. The path from a fluctuating base to a calm, large-scale world has not yet been fully traced. An everyday analogy can help this feel more familiar. A strip of film is made of separate frames. Each frame is still. When projected at the right speed, the eye does not see individual images. It sees smooth motion. The gaps are filled in by perception. If the projection slowed enough, the illusion would break. Motion would become a sequence of positions. Continuity would reveal its building blocks. Both views are valid. They simply belong to different ways of looking. This raises a gentle question about space and time themselves. Are they smooth all the way down? Or are they built from smaller units that blend together at large scales? The uncertainty principle, vacuum fluctuations, and the idea of quantum foam all point towards some form of granularity. At the same time, The success of smooth spacetime in describing the paths of planets and spacecraft suggests that any such structure lies far below direct experience. Questions like these remain open. They do not need to be resolved here. They settle into the background as attention returns to more familiar scales. Even something as simple as an apple can sit within this larger picture, resting quietly in a world where deep limits exist, whether or not they ever show themselves in what our hands can hold. In recent years, the bridge between the very small and the everyday world has come into clearer focus through a new kind of experiment. It does not feel like a sudden leap. From where we stand, it looks more like a gradual sharpening, as if something that had long been suggested in theory has slowly come into view. Several decades ago, researchers proposed an idea that sounded simple when written down. In principle, it might be possible to form an image of a single hydrogen atom, not an image in the usual photographic sense, but a reconstruction based on repeated measurements. The idea rested on a quiet sequence. An electron bound to a proton would be struck in a controlled way. Its response would be measured. From many such responses, a picture could be built of where that electron most often appeared to be. For a long time, this remained out of reach. The tools were not precise enough. The control was not fine enough. Only recently did an experiment manage to turn this idea into actual data. Hydrogen atoms were prepared carefully, always in the same state. Particles were directed toward them so that, from time to time, an electron would scatter. Detectors recorded the direction and speed after each interaction. From this information, the most likely starting region of the electron could be inferred. This process was repeated many times. Each individual event said very little. Taken together, they began to form a pattern. When the inferred positions were collected and placed side by side, they did not collapse into a single point or a neat orbit. Instead, overlapping bands emerged. Some regions filled in strongly, others remained almost empty. The result looked like a set of soft rings nested within one another, separated by quiet gaps. What appeared was not a picture of an electron as a tiny object tracing a path. It was a picture of probability. It showed where measurements tend to find the electron when the same conditions are prepared again and again. From our perspective, it feels less like a snapshot and more like a statistical portrait. Built slowly from repetition, this image updates a familiar way of thinking about atoms. It does not resemble a miniature solar system, with a particle racing around a central core. It looks more like a cloud with structure, shaped by rules rather than by trajectories. What is being shown is not motion through space, but the distribution of likelihoods. It is a quiet reminder that, at the atomic scale, nature does not follow single, well-defined paths. Even with this picture in mind, the size of an atom still needs to be placed on the larger ladder of scale. An electron behaves, for most purposes, as if it has no size that can be directly resolved. A hydrogen atom built around that electron is much larger than its central proton. The atom itself is already far below the scale of cells, viruses, and large molecules, and yet, compared with the deepest scales suggested by fundamental physics, it remains very large. There is still a wide gap below the atomic world. The lengths associated with atoms sit many steps above the scale where space and time themselves may lose their smooth character. Understanding atoms does not mean that the base of physical reality has been reached. It only marks one more rung on the descent, a region where structure becomes stable enough to support chemistry and materials. At the same time, this atomic scale is where the everyday world begins to take shape. Atoms combine to form molecules. Molecules assemble into solids, liquids, and gases. This naturally raises a gentle question. Why are atoms this size, and not vastly smaller or larger? And why do atoms of the same element share the same characteristic size, no matter where they are found? To follow that thread, it helps to look back to an earlier picture. one that predates the modern quantum view. For many people, the word atom still calls up a familiar symbol, a small nucleus at the center, with electrons circling it along thin paths. This image appears in textbooks, on laboratory doors, and in public signs. It is simple, balanced, and easy to draw. As a literal description of nature, this picture is no longer accurate. Electrons do not travel along fixed tracks like planets. Their behavior is better described by extended states and probability clouds. Even so, this older image played an important role. It was one of the first attempts to give a concrete mechanical picture of how matter might be organized. That picture emerged from two lines of thought coming together. One came from experiments in which particles were scattered from thin metal foils. Most passed through almost undisturbed. A small number were sharply deflected. From this, it became clear that most of the mass and positive charge of the atom must be concentrated in a very small central region. Matter was not spread out evenly. It was focused. The second line came from the idea that energy does not vary smoothly at all scales. Building on this, electrons were imagined as being bound to the nucleus by electric attraction, but restricted in how they could move. If classical physics alone were applied, the electrons would lose energy and spiral inward. To avoid this collapse, it was proposed that only certain energy states were allowed. In this picture, electrons could occupy specific orbits and no others. They could move between these states only by absorbing or emitting discrete amounts of energy. This restriction gave atoms their stability. It also explained why atoms emit and absorb light at specific colors rather than across a smooth range. From this model, a characteristic size for the hydrogen atom emerged. There was a natural distance that set the scale of the lowest allowed state. Compared with the size of the nucleus at the center, this distance was enormous. Most of the atom's volume lay far from the proton, occupied only by the spread-out presence of the electron. In a simple sense, atoms are mostly empty. Nearly all of their volume contains no solid core. What gives matter its solidity is not packed substance, but the way electric forces and quantum rules prevent electrons from being pushed into the same states. The emptiness is organized. It is shaped by fields and probabilities. Although this early model has been refined and replaced, the central insight remains. Atomic size is set by a balance. Electric attraction pulls inward. Quantum constraints resist confinement. From that balance, a stable scale emerges. This same scale appears again and again, wherever atoms form, whether nearby or across the universe. In this way, the atom occupies a quiet middle ground. It sits far above the deepest limits suggested by quantum gravity, and far below the scales of everyday objects. It forms one of the steady rungs on the ladder between the very small and the world that can rest in our hands. The picture of the atom becomes clearer when the idea of waves is allowed to enter quietly. Light had already shown a strange dual nature. At times it behaved like a wave spreading through space. At other times it appeared as a stream of particles. From our perspective, the next step followed naturally. If light could hold this mixed character, perhaps matter could as well. This question opened a new way of thinking about electrons and about the paths they might take. Louis de Broglie was among the first to pursue this thought seriously. If light, long understood as a wave, could act like a particle, then perhaps particles of matter could act like waves. The proposal itself was simple. Any particle in motion would be associated with a wavelength linked to how it moved. To make this idea feel less abstract, it helps to picture something familiar. A stretched string, held fixed at both ends, can vibrate, but it cannot vibrate in just any shape. The ends must remain still. Only certain wave patterns fit between them. These patterns are the standing waves of a stringed instrument. Each allowed shape has its own frequency and energy. The possible energies come in steps, not in a smooth continuum. De Broglie's insight was to carry this reasoning over to particles. If an electron has a wavelength, then wherever it is confined, only certain wave patterns will fit. The boundaries of its allowed region play a role similar to the fixed ends of a string. In this way, the discrete energy levels of atoms begin to make sense. They are not arbitrary. They arise because only certain wave patterns can exist. Erwin Schrödinger took this idea further and shaped it into a mathematical form. Instead of describing the electron as a small object following a sharp trajectory, he described it as a wave spread out in space. Around the nucleus, this wave could take on different shapes. Only those shapes that matched smoothly and remained self-consistent were allowed. Other shapes interfered with themselves and faded away. The image of a string can be extended again. If a vibrating string is bent into a loop, only waves that fit an exact whole number of wavelengths around the loop can survive. Waves that do not fit cancel themselves out. In a similar way, the waves associated with an electron around a nucleus must fit together smoothly. Only certain configurations meet this requirement. These correspond to the allowed states of the atom. In this description, the special energy levels were no longer assumed by hand. They appeared naturally from the wave condition itself. The electron was no longer imagined as a tiny planet circling a central sun. It became a standing pattern, held in place by its wave nature and by its attraction to the nucleus. From where we look now, this provided a deeper foundation for the earlier atomic models. At first, Schrödinger thought of this wave almost literally, as if the electron substance was spread out like a mist. That interpretation did not last. Further work, especially by Max Born, shifted the meaning. The wave was not a physical cloud of charge. It was a mathematical description. Its value told how likely it was to find the electron in a particular region if a measurement were made. In this view, the crests of the wave indicate regions of high likelihood. The gaps indicate regions where detection is unlikely. The wave does not say where the electron is in the ordinary sense before a measurement. It encodes how outcomes are distributed across many repetitions of the same experiment. The picture changes from a path traced in space to a map of possibilities. This shift is essential. Quantum theory does not aim to show a detailed story of motion unfolding step by step. It provides a way to calculate probabilities. The wave associated with an electron is a tool for prediction. When a measurement occurs, one outcome appears. After that, the wave description is updated. Between measurements, the wave evolves quietly according to its equation. The question of where this wave-like behavior gives way to the familiar classical world has been explored in many experiments. Interference patterns, created when waves overlap, are not limited to single electrons or photons. Larger and more complex objects have also been sent through similar arrangements. Even molecules built from many atoms can display interference under carefully controlled conditions. These objects are still very small compared with anything we handle directly. Yet they are large compared with a single particle. When isolated from disturbances, their wave nature becomes visible. Patterns appear that can only be explained if each molecule behaves, in part, like a wave spread across multiple paths. This shows that quantum behavior does not vanish immediately as size increases. At the same time, such experiments are delicate. Larger systems interact more easily with their surrounding. Air, heat, and stray radiation disrupt the orderly evolution of quantum waves. These interactions gradually wash out interference effects. The process does not involve a sharp boundary. It unfolds smoothly, making behavior appear classical as complexity grows. To sense how this looks inside an atom, it helps to imagine moving inward slowly. At the scale of the atom, the nucleus occupies a very small region near the center. Most of the atom's volume is not filled with solid matter. It is a region shaped by the electron's probability wave. In some regions, the wave is strong. In others, it is weak or absent. Shells and lobes form naturally from the allowed patterns. In this space, The electron is not thought of as a tiny object following a fixed loop. Its presence is spread out. Only when an interaction singles out a particular outcome does the electron appear at a definite location. Between such events, the wave pattern holds quietly in place. Its shape is not directly visible, but it can be inferred from experiments and from the structure of the equations. The force responsible for binding this structure together is electromagnetism. The positively charged nucleus attracts the negatively charged electron. A simple classical picture would suggest collapse. The electron should spiral inward and lose energy. The quantum wave rules prevent this. Only certain standing patterns are allowed, and those patterns keep the electron from falling into the nucleus. In this way, stable atoms emerge. A compact nucleus sits at the center. A spread-out wave surrounds it. Most of the space in between remains empty, structured by probabilities rather than filled with substance. From where we stand, this balance feels quiet and precise. And with that picture in place, another question naturally waits just ahead. Inside the nucleus itself, where several positively charged protons are held very close together, a different force must be at work. It is this force that prevents the nucleus from flying apart, and it leads the story one step deeper still. Inside an atom, the nucleus is a very small region where forces have to work quietly but intensely to keep things together. From our perspective, it is one of the most compact structures found anywhere in nature. Within a typical nucleus, protons and neutrons sit extremely close to one another, separated by distances far smaller than anything we encounter in daily life. At those separations, protons still carry their positive electric charge, and each one repels every other. Even at such tiny distances, this electric repulsion is strong. It is comparable, in familiar terms, to forces that in everyday life would be used to lift heavy objects. At human scales, that amount of force does not feel remarkable. Concentrated into a region as small as a nucleus, it becomes enormous. From where we stand, it would seem more than enough to tear the nucleus apart. And yet, most nuclei remain intact. They sit quietly at the centers of atoms, stable over long periods, forming the cores of matter throughout the universe. This contrast points to the presence of another influence, one capable of overcoming electric repulsion at very short range. In the early years of the 20th century, this puzzle drew the attention of a young theorist in Japan named Hideki Yukawa. Working in the early 1930s, he considered how protons and neutrons could remain bound together. The known forces offered no clear answer. Gravity was far too weak at such scales. Electric forces between protons pushed outward rather than pulled inward. Something else had to be acting inside the nucleus. Yukawa proposed that there was an additional force, one that operated only over very short distances. He imagined it being carried by a particle with mass. Because of that mass, the force would not reach far. It would act strongly only when protons and neutrons were very close together, and it would fade rapidly beyond that range. Within the tight confines of the nucleus, it could overwhelm electric repulsion. Outside, it would leave electric effects to dominate. This idea became the foundation of what we now call the strong nuclear force. It offered a way to understand how positively charged nuclei could exist at all. At short range, the strong force provides attraction. At larger separations, its influence falls away, and electric repulsion begins to matter more. Later developments added depth and detail, but this picture of a short range, powerful force set the direction. The strength of this force reveals itself in the energy required to pull a nucleus apart. Removing a proton or neutron from a nucleus takes work. That work goes against the attraction holding the nucleons together. The energy stored in this arrangement is known as binding energy. It is not energy in motion, but energy tied up in structure. This stored energy lies behind nuclear power in all its forms. When heavy nuclei split, or when light nuclei combine. The balance of binding energy changes. A difference appears, and that difference is released. Even a small amount of matter, if its nuclear binding energy could be fully transformed, would correspond to an enormous release by everyday standards. The strong force acts only across tiny distances, yet it creates a deep reservoir of energy. As understanding grew, it became clear that protons and neutrons themselves are not fundamental. They are built from smaller components called quarks. Each proton contains 3 quarks, as does each neutron. These quarks are held together by another expression of the strong interaction, carried by particles known as gluons. Inside a single proton or neutron, the binding is even more intense than within a nucleus. A major milestone in uncovering this structure came from experiments carried out in large accelerators. After many years of searching, evidence was found for the last missing type of quark, a very heavy one that appears only fleetingly before decaying. With that discovery, the picture of matter's basic building blocks became more complete. From this point of view, the strong interaction appears in layers. At the deepest level, it binds quarks into protons and neutrons. At the next level, a residual form of the same interaction binds those protons and neutrons into nuclei. The stability of matter rests on this layered structure. The force between quarks has an extremely short reach. Beyond very small distances, its direct effect drops away. What remains is a weaker, residual attraction between complete protons and neutrons. This is the force Yukawa was trying to describe. It is strong enough to hold nucleons together across the tiny dimensions of a nucleus, even as electric repulsion pushes outward. Because of this balance, there is a natural limit to how large a stable nucleus can become. As more protons are added, electric repulsion grows steadily. Every proton pushes on every other. The residual strong force continues to pull, but its reach does not extend indefinitely. Eventually, adding more protons spreads them over a larger region, weakening the attractive effect. Near this boundary sit the heaviest known elements. Their nuclei contain well over 100 protons packed into a region that is large by nuclear standards. At that point, the strong force is stretched thin, while electric repulsion continues to build. Such nuclei exist only briefly. They sit close to the edge, where stability gives way. This edge explains why atomic nuclei come in a limited range of sizes, and why the periodic table does not extend without end. The same interaction that binds quarks into protons also sets, through its residual form and its quiet competition with electricity, the upper limits of nuclear structure. Matter is stable enough to build atoms, molecules, and worlds, but not so flexible that any number of protons can be gathered into one lasting nucleus. And with that balance in place, the structure of matter can settle. From the depths of the nucleus outward, forces divide their roles, allowing the universe we experience to remain both stable and finite, resting on rules that do not need to be pushed any further for now. From atoms and their quiet rules, the scale of living things opens outward in many directions. From where we stand, this transition does not feel abrupt. It feels like a gradual widening, as if the same underlying order begins to express itself in new forms. Not long ago, along the banks of a river in Patagonia, something unusual came slowly into view. A piece of pale material lay partly exposed in the ground. At first, it looked like stone. On closer inspection, its texture did not quite match the surrounding rock. It turned out to be bone. As more earth was cleared away, additional fragments appeared. Over time, many such pieces were uncovered, all belonging to the same ancient creature. From these remains, paleontologists reconstructed the skeleton of a giant plant-eating dinosaur. It had walked that region more than 100 million years ago. A full-scale cast of this animal now stands in a museum hall, rising high above the floor. Standing beneath it, the human body feels small, reduced to a passing detail near the base of a long arc of bone. This single skeleton offers a simple way to sense the upper reaches of animal size. Just as galaxies mark extremes in the cosmos, living systems have their own boundaries. Bones that once lay quietly beneath layers of Earth now serve as a marker on the biological scale, reachable in a modern city with a short walk through a museum. From there, attention can drift to other records in the living world. One of the largest known organisms is not an animal at all. It is a fungus that spreads unseen beneath the soil of a forest in the western United States. Most of it lives underground, as thin threads woven through earth and roots. Only small clusters appear above ground from time to time. Genetic studies suggest that this single organism has persisted for many centuries, slowly expanding, quietly accumulating mass far beyond what its surface appearance suggests. At the opposite end of the scale, life becomes extremely small. Some bacteria are so tiny that even under a microscope they appear as faint shapes. Individual cells are far smaller than human cells, yet still vastly larger than the deepest physical limits suggested by fundamental theory. By themselves, these cells seem almost weightless. Taken together across the oceans, they form a living presence whose total mass rivals that of much larger creatures. These examples show that size alone does not determine importance or impact. In biology, numbers and connections matter. A single organism can spread across large regions and persist for long spans of time. Tiny cells, by existing in vast quantities, can shape entire ecosystems. From our perspective, living matter expresses scale in ways that are not immediately obvious. Between these extremes lie forests, insects, plankton, mammals, and human bodies. All are built from the same atoms. All follow the same physical laws. The same gravity acts on them. The same electromagnetic forces hold their molecules together. The same quantum rules operate inside their atoms. And yet, their collective behavior looks very different from the simple interactions that underlie it. From this difference comes an idea often described as emergence. At small scales, the laws of physics are relatively direct. Given a few particles and the forces between them, their behavior can, in principle, be described precisely. At larger scales, when many such particles interact, the outcome becomes harder to foresee. There is no single equation that predicts when a bacterium will begin to feed, or when a whale will begin to sing. Emergence is not an additional force layered on top of physics. It is a way of describing patterns that appear when many parts interact over time. To feel how this works, it helps to look at a system where the rules are fully known, yet the results still surprise. One such system was introduced in the 20th century by the mathematician John Conway. It is called the game of life. It unfolds on a flat grid, like an endless sheet of graph paper. Each square can be in one of two states. Time advances in steps, and at each step, every square updates according to a small set of fixed rules. The rules themselves are simple. A square may persist, disappear, or appear depending only on how many neighboring squares are active. There are no instructions beyond this. Nothing is hidden. And yet, as the system runs, patterns emerge. Some settle into quiet repetition. Others drift across the grid. Some interact, collide, and produce new structures, even though the underlying rules never change. The long-term behavior can be difficult to predict. Two starting patterns that differ only slightly can evolve in very different ways. The easiest way to know what will happen is simply to let the system run and observe it unfold. From these simple rules, shapes appear that behave like machines or signals. They can be named, classified, and combined. The rules themselves do not mention such things. They emerge only when many steps are taken. This shows that complete knowledge of microscopic laws does not automatically translate into simple descriptions at larger scales. With this picture in mind, it becomes easier to look back at nature. Flocks of birds turn as if they were a single body. Each bird follows simple cues from its neighbors. Ant colonies build complex structures, guided by local signals and chemical traces. No single ant holds a plan. The pattern arises from interaction, even in non-living matter. New properties appear at scale. A single molecule of water is not wet. Wetness emerges when many molecules move together across a surface. The same atoms can form ice, liquid water, or vapor, depending on how they are arranged. The forces between atoms remain the same. The patterns change. Some researchers extend this idea further, suggesting that consciousness itself may arise from matter arranged in sufficiently complex ways. Brains are built from cells, molecules, and atoms. The steps between atomic interactions and conscious experience are not yet mapped. There is no settled explanation. For now, it remains an open suggestion rather than a conclusion. What does become clear is that, as systems grow in size and complexity, new kinds of description become useful. The language of particles and forces still applies, but it is joined by the language of patterns, networks, and feedback. As attention moves toward the scale of living bodies, the focus naturally turns to the force that dominates interactions at that level. It is the force that binds molecules, shapes tissues, and quietly sets limits on how large and how small living forms can be. At the scale of living bodies, one force quietly shapes almost every interaction that matters. It is not the strong force that binds nuclei, and not gravity, which gathers planets and stars. It is electromagnetism. From where we stand, this force forms the background of nearly every signal, every sensation, and every internal process that keeps a body alive. Electromagnetism appears wherever electrons move or are shared, wherever charges attract or repel one another. A nerve impulse begins when charged atoms cross a thin membrane inside a neuron. Channels open and close. Ions flow in and out. The electrical balance across the membrane shifts, and a signal travels along the nerve fiber. When a heart changes its rhythm, coordinated electrical patterns spread through muscle cells, guiding each contraction. When skin touches skin, the sensation arises from tiny molecular structures responding to local electric fields. Even the simplest actions depend on this constant push and pull. Electromagnetic forces hold atoms together in molecules. As electrons are shared or transferred, those molecules assemble into membranes, proteins, and long chains such as DNA. The same forces allow molecules to recognize one another, bind briefly, react, and then separate again. At this level, electromagnetism presses, pulls, repels, and mixes. It quietly holds structures together and guides how they change. Because of this, electromagnetism becomes the dominant force at the scale of cells, tissues, and organs. Gravity is present, but its influence on individual molecules or ions is negligible by comparison. The strong and weak nuclear forces remain confined within atomic nuclei, shaping decay and fusion, but not directly steering chemical reactions. For the everyday work of a body sensing, signaling, and sustaining itself, electromagnetism carries most of the load. Once this is seen clearly, electromagnetism can also be used to think about the size limits of living things. At the very small end, a living system must be complex enough to perform a few basic tasks. It needs to store information, copy that information, and carry out chemical reactions that bring in energy and materials. All of this relies on arrangements of molecules and the electric forces between them. If a system becomes too small, there is simply not enough room for the necessary machinery to coexist. At the opposite end of the scale, large living bodies face a different set of constraints. In animals, Signals must travel through nerves and chemical pathways quickly enough to coordinate movement and response. A predator must change direction in time. A prey animal must sense danger and react before it is too late. These reactions are built from chains of electromagnetic events inside cells. As bodies grow larger, the distances signals must cross increase, and coordination becomes more difficult. Plants and fungi follow another pattern. A giant tree or an extensive underground fungus can grow far larger than any land animal. These organisms do not rely on rapid whole-body motion. Signals can move slowly through them without immediate danger. Delays that would be fatal for a running animal can be tolerated. In this way, the same underlying force sets different size limits, depending on how quickly an organism must sense and act, beyond signaling. Another constraint appears for large animals on land: heat. Every cell carries out chemical reactions that release energy. Some of that energy performs useful work. The rest becomes warmth, taken together across a body. This leads to a steady production of heat that must be released into the surroundings. Each cell can be thought of as a tiny engine, always running. As the number of cells increases, heat production increases as well. Heat escapes through the surface of the body, spreading outward into air or water. As bodies grow larger, volume increases faster than surface area. From our perspective, this imbalance makes overheating a serious risk for very large animals unless special adaptations evolve. Some of these adaptations are easy to notice. Large mammals may have broad surfaces that release heat efficiently, or reduced insulation that allows warmth to escape. Even so, there appears to be a practical upper bound on how massive a land animal can become while still shedding heat fast enough. Beyond that range, keeping cool becomes increasingly difficult. These limits at the scale of living bodies sit alongside another story, one about how size itself is defined and measured. For much of human history, units of length were tied to the body or to the land. A foot, a thumb, a day's work in a field. Such measures were practical, but they varied from place to place. Later, there was an effort to ground measurement in something more universal. Length was linked to the size of the earth, and then refined again as tools improved. Eventually, the definition of length was tied to the speed of light. Distance became connected to a constant of nature rather than to a physical object or a particular location. This quiet shift links everyday scales to much deeper ones. The same constant that defines ordinary distances also appears in the expressions that describe the smallest theoretical lengths. From our perspective, the space of rooms, roads, and bodies is connected to the deepest levels of physics by long chains of scale, built from the same underlying quantities. Most of daily life unfolds within a narrow band of size. Human bodies stand within it. Tools and rooms are shaped around it. Within an apple, cells occupy a much smaller range, while the fruit itself still fits easily in a hand. This is the region where electromagnetism, chemistry, and thermal balance come together to support living structure. Looking inside, a single cell reveals a kind of crowded order. A flexible boundary separates inside from outside, allowing selected substances to pass. Within, long molecules carry instructions. Other molecules act as workers, builders, and repair crews. Energy processing structures convert fuel into usable forms. Each part plays its role, and all depend on the arrangement of atoms and the electromagnetic forces between them. The image is often compared to a small city. There are boundaries, energy centers, transport, and maintenance. The comparison is imperfect, but it helps fix the scale. In a space far smaller than a grain of sand, a complex web of activity unfolds, guided by chemical rules and electric forces. At the scale of meters, those same rules build tissues and organs. At still larger scales, another force begins to dominate: Gravity slowly takes over as the main shaper of structure, drawing matter into landscapes, planets, and worlds. And with that transition, the focus can drift outward once again, from the living body to the broader structures it inhabits. Far above the scale of atoms and living cells, gravity begins to shape structures bright enough to light entire systems of worlds from where we stand. This is the region where mass gathers slowly and light becomes a lasting presence rather than a brief spark. One way to sense the size of a star is to imagine a slow journey across its surface. A small craft hovers near the sun's north pole and begins to drift southward, moving at a speed familiar from an ordinary drive on Earth. Beneath it, the surface does not appear smooth. It is patterned with broad granules, where hot gas rises and cooler gas sinks. Dark sunspots open like deep wells. From the edge, loops of glowing gas arc outward. Vast structures of plasma stretch far above the surface, reaching distances that feel difficult to hold in mind. At this gentle pace, the journey itself becomes the message. Crossing even a fraction of the sun's surface would take a very long time. The bright disk that moves easily across the daytime sky is, in reality, an object so large that familiar speeds barely make progress across it. Its shape is held by a balance that persists quietly over immense spans of time. Gravity pulls inward. Pressure from hot gas and light pushes outward. This balance is what allows a star like the Sun to exist steadily for billions of years. Gravity prevents the material from drifting away. Energy released deep inside prevents collapse. The visible surface traces the meeting point of these opposing tendencies. The same gravity that shapes this balance also anchors planets in their paths, guiding them around the star without the need for any further instruction. The Sun also dominates its system simply by being massive. Nearly all the material bound to the solar system resides in the star itself. The planets and smaller bodies share only a small remainder. This concentration explains why the star sets the gravitational tone. Everything else responds to it. To learn what happens in the Sun's core, ordinary light is not enough. Light produced there scatters countless times before escaping, taking an extraordinarily long time to reach the surface. Another messenger carries more direct information. Nearly invisible particles stream outward from the core and pass through matter almost untouched. Catching even a few requires patience and careful isolation from other signals. Deep underground, far from surface disturbances, detectors have been built to wait for these rare interactions. When one of these particles leaves a faint trace, it offers a glimpse into the processes at the star's center. Over time, such measurements have confirmed that the Sun's steady glow is powered by nuclear reactions deep within. Even while revealing subtle behaviors that point beyond earlier expectations, at the heart of the star, matter exists in extreme conditions. Hydrogen nuclei are pressed together at tremendous temperatures and pressures. In that environment, they combine to form helium, releasing energy. This energy flows outward, step by step, until it emerges as warmth and light. The rate of this process is vast by everyday standards. Yet the star changes only slowly, because its total mass is so large. Stars of different masses follow different paths within this same framework. Some are just massive enough to sustain fusion, glowing faintly and steadily. Others are far more massive, shining intensely and living shorter, more turbulent lives. In the largest of them, outward pressure from light becomes so strong that material is driven away. If a star grows too massive, it cannot hold itself together. It sheds matter until balance is restored. In this way, stars occupy a band of allowed sizes. Below a certain mass, fusion never begins. Above another, radiation overwhelms gravity. Between these limits, stars persist by maintaining their internal balance. Gravity also shapes the clouds from which stars are born. Vast regions of gas and dust drift through galaxies. Within them, slight variations in density can grow over time. Material gathers. Regions collapse. New stars and clusters ignite. The same force that holds a star together also prepares the conditions for its birth. At the centers of galaxies, gravity gathers matter in a more extreme way. There, enormous concentrations of mass reside in compact regions. Nearby stars move rapidly, tracing unseen centers through their orbits. These objects represent another expression of how matter behaves when enough of it collects in one place. A simple thought can link these cosmic scales back to something familiar. If an everyday object were somehow expanded to the size of a star and given enough mass, gravity would begin to reshape it. Pressure would rise. Temperatures would climb. Ordinary structure would give way. The object would no longer be solid. It would become a glowing sphere of plasma. Over time, fuel would be consumed. When the balance shifted, gravity would again decide the outcome, leaving behind a dense remnant beyond individual stars. Gravity organizes matter on still larger scales. Stars gather into galaxies. Galaxies gather into groups and clusters. These clusters connect along vast filaments, leaving large regions relatively empty. The resulting pattern stretches across the observable universe, forming a web-like structure that emerges slowly over cosmic time. On these scales, gravity shows its distinctive character. It is weak in any single interaction, yet it acts across immense distances and long durations. Small differences accumulate. Structure grows gradually. Other forces fade into the background. Electromagnetism and the nuclear forces no longer shape the large picture. Gravity becomes the main architect. There is, however, a limit to how far its influence has spread. Because the universe has a finite age and signals travel at a finite speed, only a certain region can have been in contact since the beginning. Beyond that horizon, there may be more space, but it remains out of reach. When attention shifts to very large scales, the universe appears smooth on average. Clusters and filaments stand out locally, but beyond a certain scale, their differences blend together. This smoothness, combined with the expansion of space, helps explain why the night sky is dark and why light from distant regions has not had time to reach everywhere. To account for the remarkable uniformity seen across the sky, many models include a brief early period when space itself expanded extremely rapidly. During that time, tiny variations were stretched across vast distances. Over billions of years, gravity amplified those variations, turning them into the galaxies and clusters now observed. Today, matter is spread thinly across enormous volumes. Gravity continues to draw it together locally. But on the largest scales, the expansion of space dominates. A subtle energy associated with space itself appears to be driving that expansion to accelerate. Even if conditions were to change far in the future, the matter already dispersed is unlikely to gather back into a single whole. Across this entire range, from the surface of a star to the network of galaxies and the edge of what can be seen, the same few forces set the patterns. Their balances decide which structures endure and which fade. The constants that quietly shape atoms and apples also shape stars and the largest visible forms in space, linking the familiar scale of everyday experience to the broadest map that can be drawn, and allowing the mind to rest within that continuity without needing to follow it any further. As this journey comes to a close, what lingers may not be numbers, nor complex concepts. What remains is a quiet sense that the universe was not built around humanity, yet somehow turned out to be gentle enough for humanity to exist within it. From the deepest limits of space and time, where familiar laws begin to blur, to the vast structures of stars, galaxies, and the cosmic web, everything is connected by silent steps. A small apple, the human body, a burning star, or the wide night sky Each is simply a different pause along the same journey of scale and order. Science has not yet given us a final answer about what lies at the deepest foundation of reality, nor has it revealed the full fate of the universe ahead. Yet these very limits create a unique kind of beauty. They remind us that not every question must be answered at once, and not every mystery needs to be illuminated in haste. Thank you for spending your time with the channel on this quiet voyage. If these reflections left you feeling curious, calm, or simply wanting to keep listening, consider leaving a small interaction and following the channel. We will return to explore together more surprises, more unanswered secrets, quietly waiting within this vast and profound universe.